Okay, so one of the problems that I had hoped you could look at the recordings I made for 4.8 about antiderivative, the opposite of derivative. What did I take the derivative of to get to this point? You know? And so the idea of one of the most common ones that came up, the most straightforward ones that you can visualize quickly, is that 2x. What did you take the derivative of to get 2x? You know, and you bring the exponent down and subtract 1, that came from x squared. And that situation is an evident one, okay? So it's kind of, and going the opposite direction, we've got to talk about that. The idea of you got to raise the power by 1 now, and instead of bringing the power down and multiplying, we've got to divide by that new power now. So when you have a power situation, x to the n, it becomes x to the n plus 1, and you got to divide that by that n plus 1. And we'll talk about that there at that table that Thomas had presented. If you haven't seen that, make sure you get that out and you can take a look at that. But one of the main themes I want to talk about, first of all, I want to do an example. If you haven't seen those, get in there and take a look at them. And I hope you have your calculator with you. In just a couple minutes, I want to do integration on the calculator, on the TI-83 and 84. And I'll do one example on Desmos. So we'll have that down. So you can, if you've got a definite integral, you can tell what the answer is. And I'm going to ask you to do that on a quiz Monday, to get the answer on your calculator. And that's without necessarily using all the fundamental theorem of calculus that you're going to be able to use by the time we take the test. We'll address that, and you'll get better at it. But I'm hoping you can check your work by using your calculator, and everybody will need to be able to use a calculator to calculate a definite integral, okay? So what I want to do first is go to the iPad and do a problem that fits. It was an example that they give in the text. So I'm going to share screen and go to my iPad. And it's one that has to do with something I had mentioned in the recordings that I had made in 4.8 about the antiderivative stuff, is that every one of these terms, this is lowercase f. What we're hoping to do is what they did in the text and what I had talked about in a video, is we want to determine cap f of x. So the idea is that we're making the statement that cap f of x, if you take the derivative of cap f, you get lowercase. So that means if we're starting with f of x, we're going the opposite direction to determine what did we take the derivative of to get this. So we got to do this for each term, okay? So the idea is, first let's get that 6 over x squared into a format that we can take the antiderivative of. So we end up with, this ends up being f of x, lowercase f now, it matters. Lowercase and uppercase matters, so make sure you're meticulous about that. So that's 6x to the negative 2 minus sine x. And if you happen to have the sheet in front of you or a table of some sort, that'll be beneficial. But if you don't, that's okay, we didn't talk about it. But I want to say now we're ready to find the antiderivative of each term. So the question you have to ask yourself each time is, what did I take the derivative of to get e to the x? And that's a wonderful one, because we all know that because the derivative is e to the x, then the antiderivative is e to the x also, okay? Both, that's a two-way street. Like I say on the recording, every one of these, if they were in by themselves, would have a plus c on it, because there is a possible constant that could have come with this, okay? But we're going to ignore that and recognize at the end we'll add the plus c to accumulate all of any constants that came with this thing. We'll talk about more about that later. Okay, but now here's a situation where we've got this negative exponent. Ones we had done before, the ones that I had given were mostly had a positive exponent. You add 1 to the exponent and divide by that new exponent. So that's what we're going to do here also. I wanted to make sure I included a negative on this one. So I end up with, what do we have? We've got 6 x to the, I'm going to go ahead and take the time with writing it out on top. And then notice I'll abbreviate it on the bottom. -2 plus 1 on the bottom is -1. Add 1 to the exponent, divide by that new exponent is what you do each time. And then we come to the point we've got a minus sign. What do you take the derivative of to get sine? Okay, this is the one where you got to remember one of them is positive and one of them negative. And remember, go back to the one you know. Derivative of sine is cos, positive, positive. So that means the antiderivative, you go the other way with cos, you get a positive sign. But if you start with sine and you're taking the antiderivative, that came from negative cos. In other words, cos takes you to the negative sign. So this turns out to be, if you're doing this problem and you get good with it, you'll recognize that came directly from cos. But if I write the minus sign like I just did, then I got to do sine separately. And the antiderivative of sine is negative cos. So I'm going to write it like this. And if you've already got this down, then don't worry about it. You do it the way you do it. But you'll see the logic of there was I put the minus sign that was in the formula, and then I had to take the antiderivative of sine, which is negative cos. Okay? And now is where officially a plus c should start showing up. Okay? Now, if you don't do it until the end of the problem and put it on your final answer, that's okay. But officially, right now, when you started taking the antiderivative, the plus a constant is there, should be there, okay? But again, if you put it on at the end, that won't be marked wrong. Just remember, you might want to put it somewhere. I got to put a plus c on here when I'm done. Okay, so let's fix this up now. Next step, I got e to the x. That -1, I'll bring it up and make that a -6, and that's x to the -1 plus cos x plus c. And now let's get rid of that negative exponent. Like I've said, I don't want negative exponents in final answers. So we end up with e to the x -6 over x plus cos x. And then the general answer is plus c. There could be a constant. That constant could be 0. And therefore, leaving it off completely is one possible answer. But there's a whole bunch more, because it could be any constant at all could be attached to that. And again, one could have come from the e to the x, one could have come from the 6 over x squared, one could have come from the minus sine x when we did that. A plus c could have shown up for all three of those. But the conglomerate at the end, there's plus some constant. Any questions about that? Okay, if you haven't seen those recordings back in 4.8, make sure you do that, okay? That's important to make sure you get that down, and I work through individual situations there. All right, a second part of that section, though, is differential equations. And one of the things there is to recognize that a differential equation is that you're starting off with an equation, but typically it's noted. So let me start off with one. I don't think I did this one in the class. Let's do this one. dy dx. We're talking about a differential equation. This is in reference to what we're solving. It's going to find the original function that we took the derivative of. So this is considered a differential equation. And again, the same thing is true. This fits lowercase f. That's another way of saying dy dx. That could also be recognized as lowercase f. That could also be recognized as f cap f prime of x. So all of those are saying the same thing, all right? And if this is a differential equation and you're asked what's the solution of this without anything else, the question is asking what is y? What did you start with? What was the function you started with so that dy dx is this, okay? Notice in this situation, again, I'm going to ask you for a general answer. So that means a plus c is going to be needed. You might want to write that down somewhere, like if you're ever down an assessment or something, or writing a problem out. Remember, you got to put plus c on this at the end, okay? So in this case right here, I'm going to also add to it a particular aspect. We're going to look for a particular solution. We're finding the general solution the way this is asked, which means a plus C will be appropriate in the end. That C could be anything. But if I'm given the coordinates of a point, which they do in this set, then I could then figure out what C is. And the answer, the final answer would be whatever this answer is. Instead of plus C, I would plug in what C should be. So let's go through this first and just get the solution with plus C, and then I'll add in the extra little ditty I was talking about, all right? So that means we're ready now. That means the next step is y equals. Every one of these can't, none of the terms can be adjusted or fixed in any way. So now the next part of this solution, I'm looking at what is y, okay? Well, y equals, this is the power situation. And the rule is raise the power by 1 and divide by that new power. So that becomes x to the 2 plus 1 over 3. I'll change that 2 plus 1 to 3 in a minute. Plus 2, again, there's a 1 here. So raise the power by 1 and divide by that new power. So I get x to the 1 plus 1 over 2. And then the next one, remember what we've got. What did I take the derivative of to get 1? And that, it takes practice a little bit at the beginning, but that came from x. You know, that came from just 1x. When there's no coefficient in front of it, you can't see it. When it's 2x, it's obviously 2. But when it's 1, it goes back to 1x, so we just put an x. So this becomes 1x. And here is where plus c shows up. And so now let's simplify this. So the final answer, y, is equal to x to the 3rd over 3. The 2's cancel, so I get plus x squared. The 1 goes away, plus x plus c. And then check it. Take the derivative of it. Make sure it goes back to what you just started with. Every time, do that. It should be exactly the same every time. Look at it. 3x squared, the 3's cancel, 2x over 2, and then we got 2x, got it, and then we got the derivative of x is 1, and the derivative of a constant is 0. So now, here's the point I want to make. If I had said from the beginning that when x equals 3, y equals -1, okay? Or if a point was given, 3, -1 was given, it would say is a point on the graph or something like that. Then now you can solve for C. So if I didn't give this, this is a boundary circumstance. It's called yeah. So the idea is that what we're doing is we're finding this is a general form of the antiderivative. And the other circumstance that we added in was called a boundary condition. You know, this is a boundary condition. It's saying something about what sets the limit of what C can be. Well, this does. This is called a boundary condition. Okay, so now, so that's indicating that, so we've got this in terms of y and x and c, and if I plug in x and y, then I'll have less to c. Solve for c and I'll have it. So let's do that. Y is -1. C is, x is 3. 3 cubed over 3 plus 3 squared plus 3 plus c. All that equals -1. All right? So the idea here is let's get over everything else on the other side. Let's figure it out first. -1 equals, what is that? 27 over 3 is 9 plus 9. Is that right? No, 27 over 3 is 9, yeah. Plus 9 plus 3 plus c. So I've got 18 and 3 is 21. That gives me -22 equals c. Therefore, the answer to a particular solution for this problem is that c equals negative 21. That's not the answer. The answer is the equation with c plugged in as negative 21. So the final answer is actually this. Okay? That is the solution to this problem that says this. If it includes, if you're given a differential equation with a boundary condition, then the final answer is going to be, there's no C in that answer. You got the particular solution for that moment, okay? And the thing to do every time, I will probably ask you on the quiz on Monday to verify that it works. Verify that it's right. And there's two conditions that have to be met. One is that 3, negative 1 is a point. And two is that the derivative of that function is what you started with. So let's do that part right now. So the derivative of this function, I get dy dx, then is bring the 3 down, make it a square, divide by 3 plus 2x plus 1. And that equals, if you notice, equals x squared plus 2x plus 1, which is what we started with. All right? And we just plug in 3 and make sure you get negative 1 for your final answer. Questions on that at all? Okay, tell you what I'd like you to do right now. Well, let's go to, I don't know if you've had a chance to look at the YouTube that I put on there about using your calculator. Let's do right now, I would like to go to your calculator and do with me a problem and have you get the solution to it, all right? So what I want to do is do an integration problem, all right? Let's do one, and I'll do the one that they did on YouTube, all right? Because it's kind of straightforward. All right, so what I want to do is, let's do y equals x squared. Let's do the integral. Okay, now we're talking about, this is called a definite integral, okay? I want you to see this. This moves into section 5.2 where it's talking about definite integral. And that's why we're blurring things together here, I know. But what I would like to do is, I'd like to show you what what we're calculating here is, I want to do the integral. This is the integral sign. We're talking about antidifferentiation. We're finding the antiderivative of each term, antiderivative of a function. And that term is called integration. And this is the integral sign that we're talking about. And we're going to talk about more so in a little while. I'll say something more tomorrow, I think. I'll address it more. But this is the sum of a bunch of areas of rectangles that are under the curve. If you saw my statement on, I haven't put that up yet, but the idea is, what's happening is, this is the sum. When you get to the section 5.1, you're going to see that this is it's a smooth curve that started with an S, a sigma sign in Greek. The sigma means the sum, and it was yeah. So anyway, this is a sum symbol. That's what that S is standing for. It's kind of a curvy S. But let's say we're going from 0 to 2. Let's go to 0 to 3. It comes out to a nice even number, okay? 0 to 3 of x squared dx. Part of your thing you need to write on this is the dx. You need to share it. Everybody get your calculator out if you would. I'm going to have mine out. And what I've got is, I've got a TI-83, okay? So the format I'm using is going to be a certain format. I'm going to describe, if you got a TI-84, you'll be able to see it also, but I'm wanting to speak to those that have a TI-83, and the TI-84 will be even more obvious, all right? So what I'd like you to see is, the idea is, I'm going to do this function, and on the TI-84, you've probably got, we're going to see this is going to show up on your calculator, okay? If you got a TI-83, it's going to show up as, you're just going to get the letters of the situation. So what I want you to do is get your calculator up, and if you would, hit the math key right under alpha. It's down the left, up the left-hand side, third key down. Excuse me, math is the fourth key down if you count the y equals. Hit the math key, And if you scroll down, you can scroll down to 9, or you can just hit number 9 and it'll take you there. So Math 9 takes you, and those of you that have a TI-84, you should have this on your screen, okay? If you've got a TI-83, you have this on your screen. You've got it talking about the integral function, and you just have this situation going on, all right? So those of you that have a TI-83, the first thing you write in this sequence is the function name. So what goes here is x squared. And
Are we supposed to see your iPad?
Pardon me?
Are we supposed to see your iPad?
Oh. Thank you very much. You're good. Nicely done. Yeah, thank you for speaking up. That was totally solid. Okay, so those of you that have a TI-84, this came up on your screen. Those of you with a TI-83, you had this FNINT with a parenthesis on it. And what needs to be plugged in is the first thing you need to plug in is the function name. So those of you with the TI-84, what you need to do is the x squared goes there, that box right there. And then those of you with the TI-83, we need to denote what the function is in terms of. That is in terms of x. So for the TI-83, you put an x after the comma, and those of you with the TI-84, the x goes after the d, okay, in that box. And now what comes next for the TI-83 are the limits, the lower and upper limit, a to b. And we want 0 to 3 in this situation. So what we end up with is, for those of you with the TI-84, you plug 0 and 3 there. For those of us with the TI-83 going, we do this, okay? And hit enter after you get that. And you need the dx, you need the whole situation, but what you should have gotten, let me verify it myself. I've got x squared, comma x, comma 0, and comma 3. Close parenthesis, enter. I got 9. And what we just found was this. We've got the function, and it's the area, you guys, under the curve. My section I'm going to talk about in section 5.1, the recording I'm going to put up right after this class. Make sure you watch that. The area under the curve is what's being calculated here. So what we've got is we've got over 1 up 1, over 2 up 3, 3, 4. The curve looks like that. What we just calculated is this area right there. Oh, we're going to 3. Pardon me. We're going to 3. We're going up to 9. Pardon me. That was a bad one. So we've got this. 1, 2, 3. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going out to 3. So we've got 1, 1, 2, 4, 3, 9. So we just calculated this. Okay? That area under that curve is 9. And if you had a means of verifying it, you could. All right? Are there any questions about the procedure we just did on the function? Okay, something else I do on the recording I'm going to give you in 5.1 is I do one problem that's got the area under a particular function, and I want you to go through that with me really quickly, all right? And what I'm going to do is I'm going to show it. We'll do the area under the curve, and we'll do the actual thing on your calculator. So one problem that I asked you to do on the recording, let me go to a fresh screen. I'll tell you what, I'll do it up here so we can leave the formula. That box will stay up here. This will stay up here, and this will stay up here. Okay, so we've got a situation like this. 3 seconds. And in those 3 seconds, we figure out, I pick numbers that'll be easy to work with. All right. And we're starting from, this is time, and this is velocity, which is in feet per second. Okay. And let's say that we started at 0 seconds, and it's not realistic that this happens. I think I say that on the video. But we go up for an incredibly steady, It's just a regular increase for 3 seconds, so that at the end of 1 second, we were going 5 feet per second. At the end of 2 seconds, we were going 10 feet per second. And at the end of 3 seconds, we were going 15 feet per second. Again, that's not going to happen. But here's the deal. What I want to show you is the area under the curve. It turns out in the problem that I do with you in 5.1, make sure you see it, that's coming. The area under the curve, if this is a rate that you do, the velocity, then the area under the curve is how far you travel. It's how much of a change happened. The rate of change is on top, and under the curve is how much change happened. Do that for section 5.1 today, or listen to that recording. It's pretty straightforward, I think, and it's good. But what the thing I want to do here is point out this. Notice what the function, let's calculate the area under this curve. Across the bottom is 3. Up here is 15. We got the area of a triangle, which is 1/2 base times height, is equal to 1/2, the base is 3, and the height is 15. So we get 45 cut in half is equal to 22.5. Yes? Now, what I want to say is, what is the equation of this line that we're drawing? This line segment, but if it was a line, stop and think about it. We got 0, 0 is one coordinate, so the y-intercept is 0. What's the slope? Change in y is 15. Change in x, change in y over change in x is 15 over 3. M is equal to 5. So the equation of this line is 5t for our problem. On your calculator, plug in 5x. Write the integral right now. The integral of 5x from 0 to 3, that's what we just did, dx. Do that on your calculator right now. Those of you, remember you got to do math 9. Those of you with the TI-84, would be that. Those of us with doing the TI-83, we're going to do math 9, and we'll have this on our screen. You end up with, you plug in 5x, x because that's the variable of concern. We're going from 0 to 3. Okay? See what you get. The answer should be 22.5. Getting that? Let me do it again right now myself. So I've got math 9. I'm doing 5x, comma, x. And the reason you need the x is sometimes you do just a constant term. I'll talk about that right now, just right after we finish this. Comma, there's different reasons you do it, but, and we're going from 0 to 3 again. Isn't that special? The same as the last time, 0, comma, 3, and I get 22.5. Anybody get something different? Okay, so you guys, in sapling, when you're asked to find the area under the curve of this function from on this interval, 1 to 3, 1 to 9, 2 to 4, 2 to 6, this is what you do. Do it on your calculator in sapling. After we do the fundamental theorem of calculus, I'm going to have you do it by hand, okay? But right now, I want everybody to be able to do it on a calculator, and we'll go from there. Tell you what, one thing I said I was going to do that I haven't done yet. Let's go to. I want to go to Desmos and show you how to do it there. Okay. So let's go to this situation here. Yeah, I'm going to clear that out. Let's clear this. Let's clear these out. I'm going to do a new one. Okay. Let's get this out of here. Okay, so let's do the one we just calculated right now. All right. So in Desmos, you get the screen up. Again, you don't necessarily have to do y equals. You could if you wanted to. You could just type in the function name that we're worried about. Let's do the one we just did, right? It's 5x. So the derivative, so I want to go to integral. So the circumstance we do is we go to functions. Oh, I'm going to get this on my screen. Excuse me. I'm going to get Desmos up here. Sorry about that. Let's go to a new share. And I'm going to go to Desmos. I heard you thinking about it. Thank you for not, for the thought got me to go there. Okay, so here is the circumstance. So what I'm doing now is this bottom I've got a bunch of formulas above, pardon. But what we're going to do right now is we're going to get the keyboard up. And now what I want to do is I want to go to functions. And notice you've got all the different things. And at the bottom, you've got an integral symbol, right? Integration, integral. I apparently didn't have that up. Let's do it here. I had to have this selected on 10 first. Now I hit integral, got it. Notice where it's blinking at the bottom. It's looking for A. We did 0, and then we went up to B. I did my up arrow, and it took me there to 3. Then I'm going to go right, and our function is 5x. You could do 5t if you wanted to, but 5x is what we were talking about. And it's critical. If you do it without, I'm going to put it right now, dx, and it'll automatically set it. You see, you got the answer so quickly. And sometimes if you want to make it clear, you can get a little space in between the 5x and the dx, but it automatically read it and it's got the answer. That's 22.5. Okay? So on integration, a definite integral, you guys, when A and B are there, when those numbers are there, then the answer to your problem should be a number. That is called a definite integral. You're finding the area under a definite interval. If there's no A and B, all right, then you do the antiderivative, but there's no A and B. So the answer is going to be the antiderivative, and you got to put a plus C. You take the antiderivative of each term, okay, and you do a plus C. So that's something that we'll be addressing more and more as we move on through this stuff. Any questions about what I did there? Okay, there are several questions in Sapling in 5.1 that I put up that are asking you to find the area of the curve, or they're asking you to find the distance traveled, I think one does. But what you're doing in this situation, this is all blurring together. Pardon me for doing it this way, but I think 4.8, 5.1, and 5.2 are kind of blending. I'm going to look at the recording after class today for 5.1, and I'll put 5.2 up, and we'll talk about 5.2 on tomorrow, okay? That's going to be, and we're going to be getting things set up, get going on the problems on 4.8, and then hit the problems on 5.1. You can do it now with your calculator or on Desmos. You can do the problems that they're given. Before you had that calculator down, you really couldn't do those. We didn't have the tools yet, unless you already know the fundamental theorem of calculus, okay? So next thing I wanted to do though, clock keeps on ticking. I want to make sure we do, I did that problem, got it. I did that problem, we did the graphing calculator. Oh, I want to show you one other thing, why we put the dx. So if you notice, you guys, one possible situation for writing a function, I'll do it right now on the screen. I'm going to put the integral symbol. And let's say I wanted to find out, I'll draw the picture in just a second on the iPad. But if I had, it's possible to have, let's go from 2 to 6. If you want to do that with me, you can. 2 to 6 of the function 4. Oh, 6 minus 2. Let's stay with 4. That'll be fine, okay? So notice if I just put that, the dx is needed. Let's put the dx just for clarity. That indicates there wasn't an x in the function at all. That is a horizontal line, y equals 4. Okay, that's a legitimate function. And the integral, the antiderivative of 4, it needs to be denoted what you're in terms of. That is in terms of x. Okay, what does that graph look like? Okay. So let's stop and think about this. I'm gonna come down here and remember what the equation y equals 4 looks like. Let's do y equals 4. Okay, horizontal line. It's the horizontal line going through, and that's what this is saying. We've got the function 4. All right. Now, what is the area under the curve for 4 between 2 and 6? Okay, there's the line 4. Well, between 2 and 6, notice we've got that between 2 and 6. It's 4 high. Between 2 and 6 is 4. We're going to have a rectangle that's going to be 4, right? And a rectangle that's got at 2 and at 4, so it's going to be, that's a square. That's kind of why I was avoiding picking 4 at first. But the idea is it's going to be the area under this curve. It's a straight line, but they call it a curve. We call it a curve. It's a straight curve. Between 2 and 4 is going to be 4 by 4. And the area of this should be 16, right? It's 4 by 4. So let's go back, and you notice what the answer is to the function I had up there. That comes from the area of the curve between 2 and 6 is, and it's 4 high, 4 by 4. That's 16. So that's the important part of keeping the dx in your solution. Any other questions about that? Okay, go ahead. You got one? All right, look at, you guys, number 4 in section 5.1 is one that, if you forget about section 3.3, where we did the derivative of the inverse trig functions, you're not going to know what to do. So let me go kind of quickly here to, let's go to, I'm going to go to problem set 5.1 and look at number 4. I could have picked that at the top, couldn't I? Maybe. This isn't selected. Okay, you know what? Part of the situation is that I'm going to need to step out and get myself in student mode first, because it'll have the answer right up front. And I'm going to do 5.1 homework now, and I'm going to go to the 4th problem. And look at this situation. This is, there's 1, 2, and this type of situation, after you watch my video at 5.1, you'll see what to do with this problem, okay? It's asking for the leftmost area, the leftmost rectangle. It's talking about if you drew a rectangle here, you watch my video and you'll have the answer to be able to answer the first question, okay? And if you don't, we'll talk about it tomorrow. Let's go to question 4 though. Look at this. Find all antiderivatives of the function 14x plus 5 over the square root of 1 minus x squared, okay? Look at these other ones. 3, that one's not good. Here's this one, it's a 9 minus x squared. You can find the antiderivative of each of those terms. Look at this one. We got 2x squared plus 9. You can find the antiderivative of each of those terms. But on number 4, you've got this special situation. And if you remember, or look it up, I've got it, it'll be on the table that we put up there, Thomas's chart that we have for derivatives. The derivative of, this is inverse sine function, okay? The derivative of inverse sine is 1 over the square root of 1 minus x squared, all right? So that's a special case and you need to recognize that. Others that they slip in here and that I will be possibly asking too is inverse tan. Inverse tan function is 1, the derivative of that is 1 over 1 plus x squared. If you look on the form that the table of derivatives there that we had, that's listed also. So the antiderivative then, if you're given lowercase f and you're asked to find the antiderivative, this one and the 1 plus x squared on the bottom is also it's the inverse trig function that you've got to be thinking about, okay? The others are all, what's the antiderivative of this term, from 2 to 3. So it's a matter of area under the graph. So the idea is you plug this into your calculator and A and B are 2 to 3. This is your f of x. Plug it into your calculator from 2 to 3, all right? And plug this in for your function. Make sure you remember the dx, all right? This next one. This is the function. You take the antiderivative of this from 1 to 3, all right? You don't have to do it by hand. That's going to be section 5.3, okay? All I want you to do with these is plug it into your calculator and get the answer, or use Desmos, okay? Plug it in. So one of the calculators somehow plug this in as a function from A to B, and then you get your answer. Okay? Any questions about that? Okay, you guys, that's really all I have today. Tomorrow, I want to address section 5.2. I'll put that up. Look at 5.1 recording. I'm going to turn it on right now. It's already done. And if you want to watch it right now, you can. But the idea is get ready, because with 5.2, we're going to be talking about the area under the curve, the antiderivative, integration. All those terms are talking about the same thing. You need to get familiar with it and be able to do those things on your calculator, okay? If you've got questions at all, let me know. I'm going to go ahead and drop off. I'm going to slip over to the Zoom office hours, and I'll be there until 12:30. All right? So if you've got any questions at all, that's where you can get me. Try these problems. Watch the video. They're fairly short, you know. 5.1 isn't very long either. So feel free to take a look at it and see where you get from there. All right?